Dear Professor Chu, dear Mrs. Chu, dear guests, dear students, dear colleagues, my name is Katrine K. Andersen, and I'm the Dean of Research at DTU, and it's my great pleasure to welcome you to this DTU Ørsted lecture. I'm especially honored to welcome Nobel laureate and former Secretary of Energy of the United States, Professor Steve Chu, as our speaker today. Professor Chu is a professor at Stanford today of both physics and molecular and cellular physiology. So I think in that regard, you really span also several of our strongholds in our scientific endeavors. And as just a spot-on match, we're very happy to have you here for this lecture today. DTU Ørsted lectures have since 1998 provided a platform to invite distinguished and leading scientists in the realm of science and engineering to stimulate new thoughts and introduce groundbreaking research to DTU, to the audience at DTU. The Ørsted lectures are named in commemoration of Hans Christian Ørsted, the founder of DTU, who amongst other great achievements was the first to describe the relation between electricity and magnetism in 1820. And I think this is really something that humanity has benefited greatly from ever since. The mission of DTU to develop and create value using the natural sciences and the technical sciences to the benefit of society also dates back to Hans Christian Andersen. Andersen. Well, we have a very knowledgeable provost. Thank you. Actually, we just discussed before, so many people are called Andersen in Denmark. So Hans Christian Ørsted, I think we should tribute our. I think when you look at the impressive achievements of Professor Chu, as well as his scientific focus area, it fits extremely well with this mission dating back to Hans Christian Ørsted, to be to the benefit of society. In my opinion, in my view, that really also characterizes much of what you've done in your career. So we're looking very much forward to hear from your very impressive experiences throughout your career. To the benefit of those who will not be here today, the lecture is going to be recorded on YouTube, as I just said. And after the lecture, you're all invited to join us for a reception just outdoor here. I should probably also say that the audience today, we have one full auditorium here. We have two more full auditorium next doors. So we're very, very happy that so many of you have chosen to join us for this lecture. And with these words, I will give the word to Professor Jens Nielsen from the Novo Nordisk Foundation Center for Sustainability to give a more formal introduction to Professor Chu. Please, Jens.
Thank you, Katrine. So I'm very happy to introduce our speaker of today, the Ørsted lecturer. Steven Chu received a Bachelor of Science in Physics from University of Rochester in 1970, a PhD in Physics from UC Berkeley in 1976. And after that, he joined the Bell Labs, and in 1987, he became professor in physics at Stanford. At Stanford, he also served 2 terms as head of department of the physics department. At Stanford, Chu also initiated, together with others, the BioX program, which focuses on interaction between biology, medicine, and other natural sciences for innovation, particularly towards biology and medicine. In 2004, he was appointed director of the Lawrence Berkeley National Lab at DOE. It is a Department of Energy National Lab. And under his leadership, the laboratory increased its focus on renewable energy, such as biofuels and solar energy. Chu's early research focused on atomic physics by developing laser cooling techniques, and this is also for what he was awarded the Nobel Prize for in 1997. In 2009, Chu was appointed as Secretary of Energy in the Obama administration. One thing that is fascinating is that during his term as secretary, he continued his research, and we heard yesterday that I think he published 20 papers. I still remember that in 2012, after he had served several years, I was reading a review paper with him as one of 2 authors published in Nature. In 2013, Chu resigned, but warned strongly about the dangers associated with global warming caused by the extensive use of fossil fuels. And he was quoted saying, I really like this quote, I think many of us have heard it before, the Stone Age did not end because we ran out of stones, we transitioned to better solutions. And so this is again an argument for why we of course have to find alternative solutions to fossil fuels. Steve Chu returned to Stanford, where he became professor in physics and professor in biochemistry and molecular biology. And he is a very strong advocate of research in renewable energy and nuclear energy, arguing really that new energy solutions are needed. And I'm sure we're going to hear more about that. Professor Chu has received numerous awards and recognition besides the Nobel Prize. He received the Humboldt Prize and several honorary doctorates, including from Boston University, Yale, and Harvard. Chu is member of the National Academy of Sciences, foreign member of the Royal Society, and several other academies in the US and abroad. So with this, please help me to give a warm welcome to Professor Steven Chu, who is a fantastic scientist, but also a fantastic role model for us scientists in terms of showing us how we can engage in energy and science policy with the objective of saving the world. So please.
Can you hear me? It's good. Okay, good. Thank you for the kind introduction. It's a pleasure to be here. I do want to make one small correction. It was about 38 papers, but of which 6 were already in the mill. So, so one would have been a record for a cabinet member. And people ask me, how do you find the time to do this? And I said, well, I had lots of hobbies. And if we can turn this down, I had lots of hobbies, and all of them I gave up. I stopped reading books. I stopped watching movies with my wife, watching movies on airplanes. I worked all the time, and my only hobby I wasn't willing to give up was doing science. And so it was so nice to discover what they paid me for is something I really wanted to do. In any case, let me just begin with my lecture. Very, very briefly, I'll talk about some risks of climate change, a little new data you may or may not have heard of, and then how science and innovation can really spearhead the way to a more sustainable world. So first, climate change. This is old data, 1880 to 2016, I believe. And it's the average temperature of land and ocean surface, and temperature has been increasing. When I was in Washington, D.C., much was made about this slight plateau in the increase between about 2001 and 2012, maybe 13. And the message was the climate scientists really don't know what they're talking about because they didn't predict this plateau. They didn't talk about what happened before then because they would have to then say the temperature has been increasing. But that was the discussion. I should also say that there has been a 1 degree centigrade rise since 1975. So although we talk about the Industrial Revolution, most of this has occurred only in the last 50 years. So let's go to the plateau. And why did the climate models miss this? And so what people were doing is they were dropping these Argo floats all around in the ocean. And these floats would measure the surface temperature. And they would go down and progressively measure the temperature and salinity of the ocean. They would come up to the surface. They would radio back the information every 10 days, and they would operate until their batteries left. Now you could, oh, by the way, just for those of you who are wondering, we dropped the yellow thing, not the thing in white. And you could say a few of these floats aren't going to tell us much about the ocean, and you would be absolutely right. So you drop a lot of them. And so this was the coverage. And the different colors are from different countries. So many countries around the world were taking part in this. And what they discovered was something that was a great relief to scientists. Energy is conserved. The radiation hitting the Earth, the energy hitting the Earth is monitored by satellite very accurately. not only in the visible, but the infrared, cosmic rays, charged particles, you name it. Everything being measured, including radio frequencies. And you can make reasonably good estimates of how much heat was being re-radiated back. And so the question was, we know that the greenhouse gas effect is real. Where did the energy go? And the answer is very slight, subtle changes, not predicted by climate modelers, was that it increased the ocean mixing. The bottom of the ocean is very cold, and it takes a long time. How long, we don't exactly know, but the estimate is somewhere between 100 and 200 years to warm up. And so this is data taken from 2006 to 2014, and there we have it. The mystery is essentially over. So you can ask other questions. Are glaciers melting? Is the sea level rising? And there's a simple answer. The answer is yes. Again, we have satellite data that is giving very, very alarming evidence. What happens is that as the local mass in the Earth changes, it perturbs the orbits of satellites. And in this data taken with a pair of satellites that go around in a polar orbit, so it gets to sample the entire Earth time and time again, they found out that the mass in Antarctica, the total mass of the ice, is decreasing. The yellow shows little increase, but in this time period, 2002 to 2009, it stopped increasing the last half dozen years. Western Antarctica, where you see the deep blue, the ice is running off unexpectedly fast. Some of the glaciers are going at 4 kilometers a year. That's no longer glacial speed, or a new definition of what a glacier moves at. And the big surprise was Antarctica was supposed to gain in ice mass, because there would be more evaporation, more precipitation in the form of snow and ice, but Antarctica is cold, so it should actually have gained in ice. And so it's losing ice, and it's accelerating its loss of ice. So this is very surprising. As a matter of historical record, 1 degree warmer than we are today, we knew what the sea level was because we can radioactively date the seashell creatures that live between land and ocean. So that we know when they died, we know what the sea level averaged around the world is, and it is 6 to 9 meters higher than today. That is disturbing if you live in a place like New Orleans or Delft or anywhere else. We used to think it would take thousands of years for this to happen. Now we're no longer sure. It looks like maybe 100, 200 years, and you can get the bulk of this rise. So again, one underestimated what is likely to happen. So again, I emphasize that there are huge uncertainties here. And so we still don't know. But we err on either side, and in this side, in both of these things, it looks worse than we thought. Okay, so what else? The world is under increasing water stress. We know in the United States, our wells have to go deeper and deeper. The Ulagala aquifer that was put there in the last ice age from North Dakota down to northern Texas, in the southern part of that aquifer, it's 90% gone. It is vanishing so fast that Texas actually passed the state law that told farmers they were only allowed to draw a certain amount of water from their wells on their own land. This is Texas, that they're willing to tell the farmers on their own land what to do. And it was a state law, not a federal law. This is how serious water stress has become. In California, we're terribly worried the fact that the spring snows become spring rains. About 30% of the water supply comes from snow stored in these areas. And so you'll go from flood to running out of running out of fresh water in June, July, where the crops need, or August, where the crops need the most. So all around the world, we're anticipating water stresses. We mine for water, meaning we find a new aquifer, we drill into it, we deplete it, we go to another aquifer. That plus changing weather patterns mean that agriculture around the world in certain areas might go under stress. If it's in a country that's not completely stable, you get more refugees. Europe is still not sure what to do with the 4 million refugees from Syria, but if we're looking at sea level rises of 6 to 9 meters, 10% of the world's population lives within 10 meters of sea level. Okay, the world's population is about 7.5 billion. So you're now looking at hundreds of millions of potential climate refugees from failed agriculture, water supplies, and sea level. So this is a serious problem. So this 2,900 gigatons of carbon dioxide is the probability, again, it's not a firm prediction, but the chance, this is what you need in order to stay below 2 degrees with a 2/3 chance of staying below 2 degrees. Notice on the y-axis is cumulative worldwide greenhouse gases. What you mean by that is you emitted, and let's say you emit some more in 2018, that counts for the next about 30,000 years. So by the end of 2000 and let's say 50 or 2100, suppose we're at 10% of carbon emissions today, not good enough. Because it all accumulates from here, at least for the next 35,000 years. So that's something most people don't appreciate as well. They don't appreciate what we've done already. We don't know what we've done because it takes 100 to 200 years to warm up the ocean. And it's a cumulative effect. If you stop emitting sulfur dioxide and nitrogen oxide, the lakes and streams clean up in 10 years. So, but this stuff doesn't clean up in less time. So that's where we are. We're over 400 parts per million CO2. If you consider methane and hydrofluorocarbons and everything else, we're at 490. The goal was 450. The real goal was try to stay under 1.5 degrees before the Industrial Revolution, which is really 400. That's passed. We will likely go over 550, probably 600. The founder of Taoism said, if you don't change direction, you will end up where you're heading. That's a bit of wisdom that Yogi Berra, the great American philosopher of the 20th century, might have said. And so this is where we're heading. All right. Again, 3/4 of greenhouse gas emissions only in the last 65 years. It's a very recent phenomenon. All right. How does science and innovation make clean energy and a clean environment a low-cost option? First, I'm going to restate this quote. Before I do, another quote is, our ability to find and extract oil and natural gas will likely keep pace with demand for 50 to 100 years. Even if you're projecting India, China, other countries, then sub-Saharan Africa getting more prosperous, we're not going to run out of oil and gas. The Stone Age came to an end not for lack of stones, and the oil age will end not for lack of oil. This was said by Sheikh Yamani, who is a former Saudi oil minister. Let me assure you, that's not why he's the former Saudi oil minister. What he really meant, I think, is that if you do find a better solution, then you don't look at the oil and gas in the ground and say, stranded assets, what a shame. We don't look at all the stones on the ground and say, stranded assets. Okay? And so you have to find a better solution. That better solution could include the price to society for carbon emissions and climate change, but it has to be a better solution, which means an economically better solution. The corollary is if you don't find a better solution, the oil and gas, and maybe even the coal, will come out of the ground. If you're sitting on many hundreds of billions of dollars of assets, the temptation not to bring it up is too high. So it has to be ultimately a market force that says we don't need this anymore. All right, so energy efficiency is 1/3 of the solution. You can do it everywhere in transportation, industrial processes, building cities, agriculture. Denmark is a prime good example of how you do this. But let me also remind you that about 30% of the greenhouse gas emissions around the world is from agriculture, land use, and forestry. And much of that, of those colors of nitrogen oxide, methane, these are methane from cows in the front and the back end, for example. Agriculture debris, over-fertilization, these are some of the things. The amount of greenhouse gases from agriculture and land use equals that from electrical production. Now, there is an opportunity, and DTU should look at this. There's a huge opportunity to use genetic engineering, especially the very powerful new methods that have been invented, and do high-throughput manipulation of the microbial and gene plants to increase the productivity of the plants beyond what you can do with artificial fertilizers. You restore what people call, quote, the soil fertility. And actually, a lot of the soil fertility means you are putting carbon back in the soil. Ever since agriculture was started, we've been depleting carbon from the soil, and this is a significant carbon sequestration step, but it also increases agricultural productivity. I just want to mention that just as we've just learned in the last decade that the microbes in your gut are not only there to digest food, but they have a very intimate and largely unknown relationship with your immune system and your cognitive ability. And believe it or not, your ability to recover from a stroke. Microbes in your gut. You have more cells, microbes in your gut than you have human cells, by the way. So to a microbe, a bacteria, you're just the carrier for them, okay? So similarly, the amount of microbes in soil is up to 1 billion bacteria per gram of soil, tens of thousands of different organisms in some sort of relationship, a tug of war, and fungal microbes. And there's an intimate relationship between the microbes in the soil and the plant and the nutrients it takes in. And especially around the first millimeter of soil, you have these rhizospheres. And the plant itself actually has microbes within it. And so for the first time ever, we're now beginning to be able to begin to understand what is going on. We're beginning to understand how to cultivate and isolate the microbes, so it's not just metagenomics. And so it's very exciting. Can you engineer these microbes and the plant so they get more nutrients and assist in nitrogen fixation, among other things? And the dream would be to have annual crops like corn, wheat, and so on become perennial crops that fix their own nitrogen. So this is something that I think science should take a really good look at. There's an opportunity. Other good news is that wind and solar energy are coming down. This is an estimate of the levelized costs of energy, of wind in various sites in the United States, $32 to $62 per megawatt hour, 3 cents to 6 cents a kilowatt hour, backing out the subsidies, the wind production tax credit, the investment tax credit. Solar, $4 to $6 per, and the estimate of combined gas cycle is in the same range, assuming what the gas prices will be for the next 50 years, the lifetime of a new plant. That's a guess, but if you guess $4 a million BTU, I think in Denmark it might be 12, I'm just guessing. If you assume $4 a million BTU, that's the cost of natural gas electricity in the US. We have very good wind, we have very good solar, we have very good natural gas. And so these subsidized costs are going down. And so in the best sites around the world, we're already seeing 3 cents a kilowatt hour. In fact, incredibly low bids. The lowest is 1.79 cents a kilowatt hour for Saudi Arabia solar, but that was partially subsidized by UAE. But 3 cents a kilowatt hour in good sites, costs will continue to decline to 2 cents a kilowatt hour. I advise Shell, the shell engineers think maybe 1.5 cents to 2 cents in 20 years for good sites. So this is happening. But now wind is big in Denmark, and so just so you know, Great Britain just had an auction for offshore wind, bidding 15 megawatt turbines. These are 276 meters tall. This is offshore, but look at the price, 5.75 cents a kilowatt hour were accepted. And so now, these do have a subsidy, but the national grid, Great Britain, expects wind, offshore wind, without subsidy will be the cheapest form of energy maybe 20 years from today. So again, these are all good signs. Now Europe and Denmark, most of the United States are turning their back on nuclear fission. Now I just want to make a slight plug for this. Only not because nuclear is good and it's not without risk. Nuclear waste is an issue. Nuclear proliferation is an issue. But if you look at the last quarter of where your energy comes from, including process heat, and you need energy on demand. And so one looks at that, until we have other technologies, and I will talk about that, nuclear is there. This is taken from a recent article from Lancet of looking at the deaths per terawatt hour of burning lignite, coal, gas, oil, and nuclear. Deaths per terawatt hour, serious illnesses. And this is before the risks of small particulate matter were known. And I will talk about that later, but the ratios are really very different. And so the ratio on the right-hand side are the death ratio. So what nuclear has going for it is that it is much safer than burning coal or lignite or oil. Well, no one burns oil anymore, but it's just too expensive. But in any case, but let's go on. You know, wind is great. This is going down in price, but the wind doesn't blow 100% of the time. And so you need backup generation. You need enhanced transmission, distribution, energy storage. So what do you need for that? Well, in California, we're almost 30% renewable energy today, of which wind and solar are the larger fraction. It's not hydro. It's easy to be hydro. You know, Norway's 99%. Actually, Norway's about 105% hydro. They sell their extra electricity. And the 2020 goal is to be 1/3, which we will achieve. And the 2030 goal in California is to be 50%. So let me remind you that California is the 6th largest economy in the world if California were a country. And so even though the federal government is not moving in what I consider the right direction, California, New York, Massachusetts are. And now, as you go above 50%, it gets increasingly hard to coordinate the system. And it's going to be a mix of distributed generation, local solar, wind, with the central generation. As we electrify, you would have different demands with different times on the grid. All these things become very, very complicated. And so how do you manage this grid? It is manageable at 50%. I mean, Europe and California is managing quite nicely at 30%. But as you go to 50, 80%, it gets harder and harder and harder. So you're going to manage it with unstructured machine learning. So this is the Chinese Go champion who just lost to a machine. It's particularly poignant for him because he saw the AlphaGo play the Korean Go champion a year earlier, looked at the games and said, I can beat this machine. And so in the first match, he started to weep. And he said, AlphaGo afterwards, he said, sees the whole universe of Go, while I could only see a small area around me. It's like I play Go in my backyard while AlphaGo explores the universe. And what he found was that AlphaGo programmed the machine to play itself, and it began to play itself over and over and over again. And it started to learn from itself. This has nothing to do with Go experts. And it went into a different space. It's unstructured machine learning. Google also uses unstructured translation now. Instead of people who give it syntax and grammar and things like that and refine that, they used to have a team of 60 people that did Google Translate. A year and a half ago, they flipped the switch. It's now unstructured machine learning. They told the people at Google, go find another job at Google. We don't need you anymore. The machine is better. And they leave it alone. And unstructured machine learning is already finding its way into medical diagnostics. So this is a little scary because it's, you know, it's deeper than Go and translation and medical diagnostics. It can be a lot of places. And I think machine learning can also be used to automatically manage electricity distribution, learn to forecast energy use much more accurately, and do weather forecasting much more accurately, which is also key to energy forecasting. Again, I gave a talk in the Bay Area a month ago and talked about this, and immediately someone from Google came up to me and said, yes, we're working with the National Grid to do this. Okay, so it's very exciting. Okay, energy storage. Here's my favorite picture of energy storage. So you pump water when the wind blows or the sun shines, and then you've done it. You can purify water when the wind blows or the sun shines, and you've done it. And so this is the way to generalize energy storage. This is the industrial strength version, a project that has not quite got the green light, but hopefully it will soon. In Chile, northern Chile has some of the best solar in the world, and but there are no people in northern Chile. There's mining, but you want to send the electricity to Santiago and other places. So at the coastline, there's a cliff 660 meters high, not feet, meters. And those reservoirs are 600 meters above ground. And so when the sun is shining, which is only 30%, roughly 30% of the time, you pump water up the hill. And when you need electricity, either you use the solar directly or you let it come down the hill. The round-trip efficiency of running the turbines as pumps upward and then generating water downward is about 85% efficient. It's better than flow batteries. Okay? Now, the cost per kilowatt hour, if you run the numbers of the people pushing this project, it turns out to be $6 a kilowatt hour. So I rounded up a little because people are usually more enthusiastic. Chu's rule when I was Secretary of Energy is whatever the entrepreneurs or business plan is, just double the cost and it'll turn out to be about right. And so it's nearly double. And so $10 kilowatt hour. Well, the chemical cost of sales of producing batteries was a few years ago pegged at $150 a kilowatt hour, maybe $100 a kilowatt hour today. So it's better than an order of magnitude better. And for the foreseeable future, namely in the next 2 or 3 decades, I don't see chemical storage ever getting close to this, except for a few things which I'll talk about. Standard batteries, this is a plot of battery costs, $1,500, $1,000, $500 per kilowatt hour. Remember, pump storage is $10. And those triangles were Bloomberg New Energy Finance of projections about the mean cost. The green things are the Tesla S1 battery, which is the cheapest battery. And Tesla's Gigafactory is claiming once they really get rolling, I slid it back a year and a half to 2018, the cost would be $150 per kilowatt hour. General Motors actually just came up with an announcement a month ago that said their cell costs, they think, will be $100 a kilowatt hour by 2022. So for a good battery with a lightish battery, 60 kilowatt hours is probably, you're thinking 250 miles. If you can make it a factor of 2 lighter. And so this is looking pretty good. It really is going to lower the cost of electric vehicles. But this is incremental improvements. I am collaborating with a star professor in the materials science department at Stanford, Yi Cui. And the standard anode battery is made of graphite, lithium graphite. and its energy density is down here. With silicon, you can get the energy density up here. If you can get a metal sulfur battery, then those values are the theoretical maximums, but you know, halfway down, you can really get much better batteries. I want to pause here and say that the most crucial thing in my mind about batteries is you want a solid state electrolyte, so it's just not flammable. Batteries are still less flammable than gasoline, but you even want it better. And you want the charging rate to be much higher. If you have a 300-mile vehicle and you charge 150, even 120 miles in 5 minutes, then you don't care about range anxiety anymore. Okay, and you can use a service station, which means since most of the people in the world aren't rich enough to own garages, they park in the streets, that's the only way you can actually get your charge. So if you have a battery like this, then it goes viral, if the cost is coming down just from scale manufacturing. And so now what's the probability that this will happen? And I say it's very, very good. Whether it happens 5 years or 10 years from, or a dozen years from today, I don't know. Half the battery has been, the anode silicon side is about to be commercialized. It's already in companies. And so that is, the internal resistance of that side is 8 times better, means 8 times less heat. And so that's what we're talking about. You just get the cathode side, you know, 4 times better and you're there. So very, very exciting. Having said that, batteries are not as good at storing energy as liquid hydrocarbons. So here you have on the x-axis the energy per unit weight, on the y-axis energy per unit volume. Both are very important. And there in the upper right-hand corner, you see all the good stuff: diesel, gasoline, kerosene, and body fat. These are the highest density forms of chemical energy. That's why you store your energy in fat and not carbohydrates. It's a higher, good storage of energy for a mobile platform. You see where lithium batteries are. So close to the zero axis that it looks very sad. And if you get it just a little bit better, 3 times better, everything melts away because the electric motor is 95% efficient, the electric motor battery, versus 35% efficient for engine plus transmission. Actually, it's about 30, including the transmission. So lots of things happen. So that's the goal. Airplanes have gotten more efficient. On the lower right-hand side is a Boeing 707, and on the left-hand side is a Boeing 787. I saw a column in the Wall Street Journal a couple of years ago and said, well, you know, airplanes really haven't changed that much. Kind of look at them. And they kind of look the same. They're both blue, for example. And that's true. They kind of look the same, except the Boeing 787 uses 30% of the fuel as the 747, but carries 18% more, 70% more passengers. So it's as if you have a car that used to get 18 miles a gallon, all of a sudden gets 100 miles a gallon. Other than that, they're exactly the same. And it flies faster, okay? And it has more thrust, and okay. So engine technology, lighter airframes, better aerodynamics, all of this contributed. Sadly, now more people fly, but this is an example of energy efficiency. Since we're still on airplanes, I have to give you a quiz. And what does a Boeing 777, which is one of the long-range jets in the skies, have in common with a bar-tailed godwit? So that's a bar-tailed godwit. It's a bird about this big. Okay, so no hands go up. So they both can fly nonstop 11,000 kilometers. So this bird spends half a year in Alaska and half a year in New Zealand. They used to think it did refueling stop in China. They started putting little tracers on. They found a certain fraction of them fly directly over Hawaii. They don't stop. They just use it as a landmark, turn, and head towards New Zealand. At takeoff, the fuel weighs more than 50% of the total weight of the airplane and the bird. So the bird lands one skinny bird. It has a seemingly good autopilot, but I think they still need to sleep. I don't know how they drink, but somehow this happens, okay? But that is why hydrocarbon fuel is so good. It's very, very dense, and it's good for airplanes. So, you know, for a while we'll need liquid hydrocarbons. All right, now let's go to cars. We don't need cars. China's target sales for cars is 11% by 2020, and by 2032, one expects maybe 70 million EVs on the road. China is the biggest car market in the world today, bar none. And so the blue are projections in 2015 of electric vehicle sales from 2020 to 2040. 1 year later, the projection went up like this, okay? So what's going on? There was not a breakthrough in batteries. So what is going on? So there are two things, but one of the major things that's going on is the following. I have to take you back a century to just before the turn into the 20th century. There's New York City, horse-drawn carriages. 20, 30 years later, cars everywhere, no more horses in cities in the United States. So you can say, well, cars were a better technology, but think of the infrastructure you need. You need better roads, you need an oil, gasoline supply chain, you need repair shops, you needed everything. And yet, so you have this technology transition of 2 to 3 decades, which is one of the fastest we've ever seen that needed so much infrastructure. But the main driver was something different. It was pollution. What was the pollution? It was horse manure. In New York City, Manhattan, and Brooklyn, 160,000 horses producing 3 to 4 million pounds of horse manure a day. Piling up on vacant lots, 1 story high. You couldn't miss it. You couldn't help but smell it. Little street urchins would have street sweepers that well-heeled pedestrians don't have to walk ankle deep in horse manure. They make a little path for them. And so this really hastened the transition. Along came something that didn't poop. Okay, this is Beijing on a bad air day. And particulate matter, especially the smallest particles, particles less than 2.5 microns in diameter, are turning out to be especially deadly. Well, in this Lancet Oncology article, using British data, they say for every 5 micrograms per cubic meter, you have an 18% higher chance of getting lung cancer, based on a huge study of 300,000 people over 12.8 years. All right, what's the average air in Beijing? Well, it's 76 micrograms per cubic meter. So how does the risk of lung cancer scale with exposure? Well, at these levels, it's worse than smoking a package of cigarettes a day, except everybody smokes since day 0. And going inside for most people means it can be reduced to 1/2 of the outside exposure. The bigger particles can be reduced more. Those are the things that give you the sore throat if you ever go to Beijing or Delhi. But the small stuff just misses it and goes completely down into the alveoli of your lungs. And it not only gives you cancer, it gives you coronary disease, stroke, chronic obstructive pulmonary disease, all of them with about the same risk hazard. And so there's a 1-month-old Nature commentary in 2017 that says, we're expecting today 4.5 million deaths per year due to air pollution, but to zoom through the roof, because this is a recent phenomena, and it takes 10, 20, 30 years to die from this stuff. So what people are facing is, if you're in China, you have 1 child, you expect the child, if you're in a middle-class family, to go to the age of 80 or 90, and it would be very heartbreaking if that child died at the age of 40. And so this is what people are beginning to realize. This is why France is outlawing internal combustion engines by 2040. This is why Great Britain by 2040, Scotland by 2030. China has not weighed in on what they want to do. And so this is the modern day version of horse manure. I should also say that congestion in major Chinese cities is horrendous. And the only way you can get people off the streets is to make public transportation much faster and much more pleasant. And once you do that, then it's automatic. But before you do that, everybody is going to follow the American model. Big car, lots of horsepower, you know, you have the money, you can buy something like that. And so, but once you can zip around 2 or 3 times faster and stay connected to the world, you might not want to get in your own car. So this is something we've got to do. But let's go forward and say, what can you do with clean energy at 2 to 3 cents a kilowatt hour? And in particular, this changes the entire role, in my mind, of electrochemistry. And if you look at the thermodynamic limit, this is the enthalpy. The real Gibbs free energy is a little bit less, but this excludes slight overpotentials, so it's a good proxy. If you want to take electricity and you want to split water, turn it into hydrogen and oxygen, both would be very useful for energy, green energy. This is the amount you need per kilowatt hour per kilogram of hydrogen. Hydrogen now costs $1.50 per kilogram. At oil refineries are the ones who use it the most. And so that's the thermodynamic limit. And if you're 5 cents a kilowatt hour, you don't think about electrochemistry. If you're 2 cents a kilowatt hour, it gets very real. And so this is what's really changing the landscape. And for this reason, a couple of years ago, I said to myself, electrochemistry. Learn electrochemistry. So I had to learn what the words reduction and oxidation mean and way, Anyway, so let me give you an example. This is work of Junyi Lee, who's being co-directed by myself and Yi Sui. And she had this idea of what she calls an artificial lung. And what a lung does is you breathe in air, and it has oxygen. And in the alveoli of the lung, there's a transfer of oxygen into the blood, but the blood doesn't leak into the lung. So there's a membrane that prevents this from happening, but lets the gas diffuse in. So oxygen is carried to the cells by hemoglobin. Another enzyme, carboxyl anhydrase, takes the metabolism product, which is CO2, and transfers it back to the lung. And then because of the concentration gradient, CO2 goes back and then you exhale it. It's great. Works really great. Okay. All right, now let me talk about, is that a, I don't know what happened there. Oh, I know what happened, a change of, okay, so this is electrolysis on an anode and a cathode side, and it takes water and turns into oxygen plus 4 protons and 4 electrons that got shifted over by some change in font. And on the cathode side, you have protons and you have electrons, and you make hydrogen gas, and the total reaction is you're turning water into oxygen and hydrogen. And in this cartoon, you might not be able to see it, but there are these little bubbles of hydrogen and oxygen happily coming to the surface. And you put a membrane in between, and you have hydrogen, you have oxygen. It's great stuff. It works. We all learned this in grade school or high school. And the only trouble is, can this ever be practical? And now, there are rare metals that are used in this electrolysis process, but if you look at the cost of these metals, it turns out it's about 4% of the cost. The biggest cost of going to scale is real estate. It's not the cost of the catalysts, okay? So then Jun Lee said, okay, let's use this artificial lung, and can we do the following? Instead of the membrane that separates blood from the lung, can you have a polymer that separates the air or the CO2 from water? You put your catalyst on the polymer surface. The polymer is hydrophilic, so it doesn't allow the water to pass through. But because you're in water, you can actually have an electrolytic reaction. Now, suppose you're oxygen or hydrogen on the either cathode or anode side, and you're making the reaction is to make oxygen, and the oxygen has a choice. It can diffuse in a membrane, which you see down below has lots of little holes, big holes. It doesn't, the scale bar is 2 microns, so it's not going to impede gas flow, but it's so hydrophobic, water doesn't go in. Even at reasonably high pressures, it won't go in. You can either form an oxygen bubble, but in order to form an oxygen bubble, you have to nucleate, and you have to use a lot of energy to actually, for the surface tension, to actually make a macroscopic bubble that goes to the surface. Or you can just go out and into a partial vacuum, you know. Okay, so what would you rather do? Of course, you'd rather go on the gas side. So if you use this cheap polymer in electrolyte, it works. And so you can have a positive, you can have a negative, you can have water. So that's the reaction. And on those surfaces, you can do the oxygen evolution reaction, the hydrogen evolution reaction. It's all very good. This is the membrane that works. You put the catalyst on one side, you put the other catalyst on the other side. You can do this. What about the water? Well, you know, let's say you want to make a tower 10 meters high or something like that. So you want to draw the water in. That takes energy, but not really. If you make the material in there with cellulose fibers, it likes to wick and wet, and so it will draw itself automatically. The water gets turned into oxygen, hydrogen, goes up, and it draws more water. So you don't have to pump water. And so the material we're going to use is this. It's designed to wick water very effectively. Let me remind you that this is what trees do. Trees actually wick water from below using capillary action. And because it likes to wet these cellulose tubes, it can actually go up, and the limiting height it can draw water is 400 feet, which limits the height of redwood trees. That's why redwood trees don't go any taller. And what happens is the water transpires out the leaves, and it just draws up. And so the act of the metabolism is the same. So what we see now is being able to draw the water up, make the oxygen and hydrogen. We leave a little structure in there to keep it from collapsing. And oh, by the way, the gaps can be 1 millimeter or 1/10 millimeter. All of a sudden, electrochemistry becomes 3D. The rate of doing this, let's see if I have another, nope. We're also doing this for CO2 and CO. The rates of reactions are for water production and CO2 reduction and electrolysis is slightly better than the best catalyst. So the reaction rate is actually really very good because there's no energy penalty. And now you have three-dimensional, so the real estate becomes much less. So we are very excited that this. Now, all the other people inventing catalysts, we wish them good luck, because the better their catalyst, the better this will work. Because it was attacking a different problem. How do you make 3D electrochemistry? And so let me throw out something else which we have not figured out yet. But this is Nakamura, who got a Nobel Prize for his co-invention of the blue LEDs. And I've become a friend of his. And it's, you know, once you get a Nobel Prize, there's a secret handshake and a ring and everything, and you get to know everybody. And so he was saying that, and this is from his Nobel Prize lecture, he's saying that an LED laser, that's an LED, the red on the right-hand side, the laser is on the right-hand side. He says the prospect of having a laser, blue laser or violet laser, be more efficient than the LED is very real, because once you reach laser threshold, it's sucking out the excitation, and so it doesn't give it time for recombination, Auger processes, everything like that. So he's thinking 70% wall plug efficient, maybe going to 80, 90%. So think about it. Electricity, super cheap, 2 cents a kilowatt hour. Blue light, super cheap, 0.7 times higher than, 2 cents. So it's 3 cents a kilowatt hour. But you can do blue light. Think of photochemistry. Okay? Never before would you have blue photons that are cheap. And so this is a new opportunity. We're scratching our heads, beginning to think, what can we do? Just like 2 years ago, I said electrochemistry is going to be a future. Now maybe photochemistry or photoelectric chemistry, because of the opportunity of what happened in some other very different field. So again, perhaps an opportunity to think about. let me tell you about another clever idea. It's still in its nascent phase. This is led by Arun Majumdar, who was my first RPE director when I was Secretary of Energy, and he and I decided to go back. Well, my wife decided I was going back to Stanford, and Arun said, "Where are you going?" And I'm saying, "I'm going to Stanford." And he said, "Oh, I automatically assumed you were going to Berkeley." And he was from Berkeley, and so we talked, and so he said, "Okay, we're going to go to Stanford." So I'm going to very briefly say, I don't know how much time there's left, but there was a paper in Nature Communications of 2015 where someone noticed if you can take some metal oxides, like cerium oxide as an example, magnesium oxide, and if it's in a hot environment, you have a rock salt structure of the oxygens and magnesium having a very simple cubic lattice displaced. And the oxidation state of the metal is a certain oxidation state. But when you lower the temperature, it goes to a more complex structure called a spinel, where you have, instead of metal oxygen, MO is the metal and the oxygen, now you have M3O4. So the oxidation state of the metal is different. So what that means is the crystal structure begins to change the oxidation state of the metal, which then says, do you want the oxygens, this ratio of MO, it's 1:1, this ratio, it's 3:4. And so when you take the spinel compound of ratio 3:4 and make it go back to rock salt, you kick out an oxygen, okay? In addition to this, you actually have an interesting entropy handle, because now you have oxygen vacancies in the crystal or not. And so you have both enthalpy and you have entropy by undergoing a phase transition. And so Arun said, now people tried this and it didn't work very well. But by looking at more complex materials of going rock salt to spinel, so it's just not magnesium oxide, it's got a little iron, it's got a little nickel, it's got more entropy. And all of a sudden, he's finding out that in going from hot to cold and cold to hot, you split water, which means you're making hydrogen and oxygen, but you're making it thermochemically. So because of the new handle of entropy, you actually have a thermochemical way of splitting water that before you could split water at 1500 C, but that's not interesting, that's too hot. You actually, in steam reforming, make steam at 1100 C. So industry knows how to deal with 1100 C, 1000 C. And they've got this to work at 1000 C. And they're hoping to get it to work at 800 C. Now, you need to be over 750 C to have enough free energy to split water, but that's okay. 800, 1000 C is perfectly okay for the thermochemical industry. A lot to be known, reaction rates, things like this, but a very new approach to thermochemistry using both enthalpy and entropy and structural transitions, structural phase transitions on the entropy side. Again, very novel, very exciting. It may work. This is cerium oxide. This is some data. This is hydrogen yield. For the best one was an alloy of iron plus magnesium plus cobalt plus nickel and oxygen, and you're producing, milliliters per gram. It's good stuff because before you weren't producing anything unless you went to 1500 C. So again, exciting opportunity. Final thing, again, based on material science, there are new materials called metal organic frameworks, and they could be in structures like this, where those little blue things are diamines. They are the amines that are used to capture carbon in liquid amine processes, but liquid amine is run into a dead end because it has a huge energy cost. Liquid amine readily absorbs carbon dioxide, but you have to heat up the liquid to very high temperatures in order to get the carbon dioxide off. And you end up using 30% of a power plant's energy to capture carbon dioxide. So that energy penalty is an economic penalty, and it's deemed too expensive to use commercially on a large scale. if you can get the price down to $20 or say $30, including compression, you're in a totally different ballpark, because quite candidly, $30 a ton for capture and compression is actually viable, because $50, $60 a ton price on carbon means you can do this at a profit. And if you can make carbon dioxide and have sources, and if the electrochemistry does work in reduction, then you actually you're recycling the carbon dioxide. Other people trying to make cement out of this stuff without the calcium carbonate. The feedstock is silicon carbonate. And an acid plus a base process, you can maybe get calcium carbonate. So cement production, by the way, is 1.5 gigatons a year of carbon dioxide, out of a total of 35 gigatons of carbon dioxide per year, okay? Of which China is 1.2 gigatons. Okay, just China, but they're building the most. And then next comes India. So you want to capture the carbon dioxide from coal, steel, cement, petrochemicals, everything. And again, it's a phase transition. When the carbon dioxide goes on these diamines, it actually goes into a different structure. Because it's a phase transition, you can tailor very small temperature swings to capture and desorb the CO2. And that's a big deal, because that means the parasitic energy load becomes very, very low, and all the other stuff is just spectators and stuff. And so this is a company I'm on the board of. We were trying activated carbon, but we stopped doing that because that was kind of dead end. But the metal organic frameworks and metal organic frameworks in polymers actually has real potential. All right, so here's a challenge for the 21st century. What do we need to get away from using nuclear or fossil fuel? The energy storage cannot be chemical batteries as we know them today. So what we really need is to recycle the carbon dioxide from the point sources, ultimately from the atmosphere, because I think we'll go over 600 ppm. But you start with the easy stuff. You start with 10% and 20% carbon dioxide. And so what you do is you take the combustion products, which are CO2 and water. You have a thermochemical means that I told you about with the Runes tries and others. You have electrochemical, which we're looking at. You have maybe photochemical or photoelectrochemical with the cheap lasers. You have biochemical, maybe. Whatever it takes, you start making the building blocks: hydrogen, carbon monoxide, or oxygen. If you burn fossil fuel in an oxygen atmosphere and CO2, you're just making water and CO2, which is easily separated. Now you have a stream of CO2, which you can then turn into some other useful thing. So all of it helps each other. From that, can you make other liquid hydrocarbons? Because remember the 777 and the Bartel-Godwit. Those are the things you really want for the highest density, longest range transportation. And so why do you want a liquid hydrocarbon? For another good reason. You can ship it very cheaply and store it locally around the world. And how much does it cost to ship and store crude oil anywhere around the world, and the equivalent of dollars per gallon of gasoline? The answer is 2 cents. Shipping and storage. So this is your long-distance transcontinental transmission line, okay? And that means you can go to where the renewable resources are best, make the stuff there, put it on a tanker and ship it, if you can get a liquid hydrocarbon. The other alternative, which I didn't have time to put in the talk, is can you get hydrogen into an organic liquid? And the answer is yes, you can. If you can get it inexpensively into organic liquid, put the organic liquid on a tanker, ship it, put it in storage tanks in organic liquid, and when you want the hydrogen, you reverse the process. So there's a group in Germany pioneering this approach. The density of the hydrogen is equal to that of cryogenic hydrogen. Okay, so it's all about getting the chemistry really to work. But there's another possibility. Methanol is not as good as diesel fuel, but it's good enough. Okay? And so, so these are the possibilities. So let me end by reminding you of one of my favorite pictures taken on Christmas Eve, 1968. It was the first mission that orbited the moon in preparation for the Apollo 11 moon landing. There was nothing between Apollo 11 and Apollo 8. When you skip numbers, you make more progress. Well, NASA was under a schedule to get a man on the moon by 1969, so I had to skip a few missions. They orbited the moon 4 times, and they turned the capsule earthward. And the astronaut who took the picture said, "We came all this way to explore the moon. And the most important thing is we discovered the Earth." And all those pictures of the Earth at a distance remind us, number one, the moon is not a good place to live. The Earth is a very good place to live, at least from that vantage point, but even up close. And look around. There's nothing, nowhere to go. So since 1968, we have learned we're changing the climate of the planet for the worse, and we've got to fix it, because there is nowhere else to go. Thank you.
Thank you for a fantastic talk. We have time for a few questions. Should probably.
Oh yes, I love these. You can just
up here.
Oh, you're allowed to throw them. I thought the whole idea is you throw them.
Thank you, and really appreciate for your speech. And I just wonder, we've had technologies out there, but do you believe in human nature? Because I'm pessimistic about it. And some researchers suppose we are going to the worst scenario of climate change. So what's your perspective about that?
I do believe in human nature. I do believe some humans are very good and others are less good. And one hopes that the ones who do feel responsibility for people other than themselves and their immediate family and for the next generation or will prevail. We are in new territory. Nowhere has science ever told the world that what we're doing today will affect people 100 and 200 years from today. Never has that occurred in the history of human, okay? And so this is new to digest this, but we have to digest it. That, the bottom half of the population of the world, certainly the bottom quarter, will be in great peril if we don't change our course. And so I think it will work. I think more and more young people are going into this, and it doesn't have to be all science and technology, the humanist side, the law side, all this will be needed in order to figure out how to get the world to change. But so my hope is we will figure it out.
Thank you.
There's a question over here.
Hi.
Oh, sorry. Go ahead.
Sorry, Mr. Zhu. I'm Shu Xinzui, research engineer from the civil department. I'm working on non-compressor HVAC system with thermochemical materials recently. You mentioned that the energy density of fat is basically higher than lithium, but there's one question you didn't mention is that the specific power of this system is much lower. When the carrier is an electron, the transition of the energy is very fast, but the release and the absorption of gas in your case is the oxygen, and in our system is the water, which is very slow. So can you speak a word of this subject?
Well, I've been told when you ignite gasoline and diesel fuel, its conversion into water and CO2 is actually fast. 20,000 RPM if you want it. And so it depends on, but nature doesn't need to turn glucose into ATP, into ADP that rapidly. So there's no real reason for it to be metabolizing that rapidly. But we do know, in fact, that's why liquid hydrocarbons are so good. Okay, burning lithium, but the energy thing on that is burning lithium and oxygen. So burning is still a pretty good way, but it becomes a thermal engine, which then is limited to 40–50% thermodynamic efficiency. But my whole point about liquid hydrocarbons is the energy density in weight and in volume, and the fact that it can ship around the world and be stored at room temperature. And so that's the major thing that we need in order to get the really energy storage we need to go to 100% renewable. Before that, I don't see how we get to 100%. In good places around the world, you can get to 50%, even higher, but 100 is tough. So that was, I guess, did I answer your question?
Yes. Specifically, in our system, we discovered that, as you say, the water release is very slow.
Yeah.
It recalls me that your paper published in Nature last week, maybe together with Yi Cui, development of the microscope on the lithium battery.
Yeah.
That we also want to use this kind of technique to observe the materials transition in a very microscopic way, but we don't have the facilities here in the DTU. So is there the possibility that we can collaborate with
There's always a possibility to collaborate.
Okay, I think you can maybe catch up.
But anyway, but I think the higher level point is that better you have a microscopic atomic understanding of what's going on, the better you are to go further. And so for those young people in the audience, you can either get rich, you can get famous, you can get Nobel Prizes. The world can be your oyster, and you can help humankind. And there's exciting possibilities out there. I'm energized by the research opportunities that I see, and I was so desperate I was even willing to try to learn chemistry. I'm sorry if I insulted a chemist.
Okay, please, let's the last question here.
Not at all an assault when you talk about electrochemistry, because we agree in that. And I like very much your final diagram with all these kind of possibilities. You had in the bottom the bio one. And there I have a question to the engineering, the microprobes you were talking about. I see there can be a big potential, but I can also see a big danger.
Yes.
So how will you assure, if you go for this line, how will you assure that we don't start changing our whole microbiosphere?
Okay, so there are two questions. One is the more traditional fear: if energy competes with food, can you both produce energy and produce food? And the answer is the bioenergy won't ever be 100% of the energy. No one who's doing research in that, but anything that's 5 to 10% or even 1% is a welcome addition. And so now to your specific question about understanding the microbes in the soil, which is yes, the microbial engineering, yes. And so there is, one has to always be concerned about that. And I would have to say that, let me give you an example. I think there are certainly fears out there about microbial engineering or even plant engineering, that plants swap genes all the time and that you're going to change things. Not all the stuff in genetic modification, Monsanto was very tone deaf in what they did. I'll be candid. They could have done it much better. Let me give you a good example. There's in celery a natural pesticide that prevents bugs from eating the celery. And you can take that gene and you can put it into corn, you can put it into eggplant, you can put it into cotton. And when they do that, and the expression of the gene is much less than celery, it turns out no one can taste the difference in flavor, but all of a sudden you don't need the pesticides. And the third world farmers love it. BT corn, BT eggplant, BT cotton, they love it. All of a sudden, the insects aren't eating their crop. And we've been eating celery for quite a while, but the dosage is much less. You don't eat as much celery as you eat corn, but it's way less. So that's pretty good. You can actually have methods if it does, you are concerned of it going wild and things like that. And so you're also concerned actually of the bugs mutating. So there's a double-barreled whammy. So you need a couple of natural pesticides. You also have a means to actually prevent it from gene transferring away. Most mutations die, but there's always a chance it could. Now, in the United States, we have been using genetically modified crops for a couple decades, and there has been nothing that has so far come. That's not to say we should let our guard down. But in any case, there is a role for genetic modification, as there I think must be, because the amount of land we're putting under agricultural production is actually quite limited, and it's plateauing. And now, we have to get over this hump in population. The hump is probably 10 billion, maybe 11 billion. The good news is when you get rich, you have fewer kids. Automatic birth control. Due to late night TV, something to do at night, other than, you know, what people do at night. Women's education, lots of reasons. And the fact that parents don't want their kids to hang around the house until they're 60. So lots of complex reasons, but the fertility rate among middle-class people in all countries, including developing countries, is less than 2. Really less than 2. I just came from Korea, it's 1.1. You need 2.1 to maintain stable population. In Europe, aside from immigration, it's less than 2 in just about every country. So we have 2 problems. We have one self-correcting problem, but then how are you going to grow on prosperity when you don't base your economy on a Ponzi scheme? Anyone know what a Ponzi scheme is? Okay. It's, you have young people, a growing younger population to take care of the older people. And as long as the younger population is more younger people than older people, it's okay. Okay, this is not good for sustainability. Okay, so you have to have an economy that actually can deal with a shrinking population and still have prosperity. The ultimate answer is going to be robots, right? That you can have increased productivity without people. And that's how you break the Ponzi scheme. And the way you break the birth control scheme is you create wealth. Okay, and then you figure, and then what goes in between is really complicated. Because there's there and there's here, and how do you get over this hump? But I think we got to get over the hump. And just as I think we're going to have to figure out how to stop climate change, we're going to have to figure out how to let the population naturally shrink down to a couple billion, and then it's okay. But if we go to, you know, 7.5, we're going to go to 9.5 by mid-century. Yeah. Okay, sorry. Anyway.
Okay, thank you very much. I think it was very interesting to follow. Thank you.